Hello everyone, welcome to what will be pre-lecture number 33, and we're going to talk about integrated rate laws and half-lives of reactions. So thus far in kinetics we've talked about rate laws, and particularly last class we talked about how we determine a rate law from experimentally measured data, and that is great, but we can learn even more information about a chemical reaction. And so typically the way we do this is using an integrated rate law once we determine the order of a reaction. And so these are equations that relate our concentration of our reactants to time, basically. And so they are very helpful in that they can be used to determine the amount of reactant or product present after some period of time, or estimate a time required for a reaction to proceed to a certain extent. And so that can be very helpful in a practical sense for the development of chemical reactions. So why are they called integrated rate laws? It is because we integrate the rate laws, as in use calculus to derive them. In Gen Chem 2 here, we are not going to go through the actual derivation, so if you haven't taken calculus yet, don't worry, you don't need to know any of it. We'll go through what those equations come out as after the integration of the rate laws in this video, and I won't ever ask you to do calculus in this class, but for those of you that are familiar with calculus, it might be helpful for you to just add a little bit more context as to how we arrived at these equations. Okay, so if we have a first order reaction, as in our rate is equal to K times the concentration of A, and we were to integrate that, then the integrated rate law for a first order reaction turns into the concentration at any time for that chemical species is going to be equal to the initial concentration of that chemical species multiplied by E, which is our constant E, as in basically the inverse of our natural log, to the negative KT. And so again, this lowercase k is our rate constant, and then T is our time. And so if we were to graph that equation, we should be able to get a straight line if we graph the natural log of the concentration of anything at any point, and that is going to be equal to our y-intercept will be the natural log of our initial concentration minus KT. And so kind of characteristic things, if you were to graph this rate law, you should have a y-intercept that's equal to the natural log of your initial concentration. And then if you take the natural log of the concentration at any time point and graph it against that time, you should get a straight line. Okay? And so those are key things to know for our first order integrated rate law. If we have a second order rate law, so now rate is equal to K times the concentration of A squared. If we were to integrate that, our second order integrated rate law should end up with another sort of y equals mx plus b sort of situation here, where again, our initial concentration is this A sub t, and then, our initial concentration is A sub 0, A sub naught, we could call that. And then our concentration at any time is A sub t, K is our rate constant, and T is our time, okay? And as you might expect, if we were to graph that with our y-axis being 1 over our concentration, basically the inverse relationship of our concentration versus time, then we should get a straight line going up. Whereas if we were to graph this data that we collected using a first order sort of approach where we have the natural log of our concentration, the line we would get would not be linear. It would have a curve to it, right? And so kind of a key thing to take from this video is that in order to determine the rate law, one way we can do that is by graphing it versus as a natural log or an inverse versus time, and whichever one of those gives a straight line should be our appropriate rate order for our reaction, okay? Lastly, we also have zero order rate laws, And so this is essentially just a y equals mx plus b relationship here, where again, if we were to graph things, if we just have an unaltered concentration, so we don't take the natural log, we don't take the inverse, just concentration versus time. If it is a zero order rate reaction, we should get a linear fit. If it is not zero order, so for example, in this reaction, if we are decomposing ammonia on SiO2, this would not be a first order reaction, or a zero order reaction according to the data. It would be first order or second order. So, but when we decompose it on tungsten, which is W here, we know it is zero order, okay? And essentially that's what I just said there. Okay, so hopefully you can kind of notice the pattern between zero, first, and second order integrated rate laws. Something else that we can derive from our integrated rate laws are half-life of a reaction. And so let me define that for you, that the half-life of a reaction, which we typically say is T subscript 1/2, is the time required for half of a given amount of a reactant to be consumed. And so I know this can occasionally be confusing for students, where half-life would indicate, at least instinctually for some people, that a time is going to be what we report for the half-life. But in fact, it is the time to get to 1/2 of the reactant consumed. So it is not half of the time of the reaction, it is the time required to reach half of our concentration, okay? So due to different rates of different reactions and different rate laws, of course, each reaction will have a different sort of equation associated with it for calculating the half-life. These are derived in your textbook, so if you're a person who really enjoys mathematical derivations or they help you understand things, I would recommend checking out your textbook to see those. But these are our first, second, and zero order half-life equations. Something that I will point out here that is a key difference between our first order versus our second order and zero order is that in first order, you'll notice that we don't have a term for our initial concentration. So what that means is that for a first order reaction, our initial concentration is not going to basically alter the half-life of the reaction at all. However, for second order and zero order, those half-lives are going to be affected by our initial concentration of our reaction, okay? And that is something, again, that we would have to determine experimentally, like all things with kinetics, but we should be able to tell, at the very least, whether this is first order or second or zero order, depending on if the rate or the half-life of our reaction, basically the time it takes to consume half of our initial concentration, is dependent on our initial concentration or not, okay? This is a nice table that basically summarizes everything that we've talked about the last two classes. So if that is helpful for you to think about, that would be great. We're gonna spend class working on some problems related to these integrated rate laws and half-lives. So hopefully you are feeling well prepared for that. But until I see you, have a good rest of your day, and I will see you soon.